In this video, we're going to be talking about continuity. A function f is continuous at a number a if the limit as x approaches a of f of x is equal to f of a. This definition implicitly requires three different things if f is continuous at a. The first requirement is that f of a exists. This is another way of saying that a is in the domain of f. The second requirement is that the limit as x approaches a of f of x exists. And the third requirement is that the limit as x approaches a of f of x is equal to f of a. If any of the three requirements above are not met, then we say that f is discontinuous at x equals a, or f has a discontinuity at x equals a. Discontinuities can be categorized into one of three types. All three graphs below have a discontinuity at x equals a. The first kind we'll explore is called a removable discontinuity. So notice that there's just a hole here in this line and the function is defined elsewhere, so that's why we call this a removable discontinuity. Notice that I could redefine, suppose I got rid of this thing here and then filled in that gap, then notice that it would be continuous. So that's how we can think about a removable discontinuity. The next type of discontinuity is a jump discontinuity. Notice that the limit as x approaches a from the right-hand side and from the left-hand side are different limits, and so that's why we have a jump discontinuity. And the last type of discontinuity is an infinite discontinuity when the limit as x approaches a from the right-hand side or the left-hand side either equals infinity or negative infinity. That's when we have an infinite discontinuity. Example 1 says below is the graph of a function f. Identify any discontinuities and their types, provide correct reasoning. So let's go from left to right, and I'm going to kind of highlight these. Here, notice that we have that going on, and so there is a removable discontinuity at x equals negative 3. There's another one at x equals 1. So notice that we have a hole there and the function's defined somewhere else. At x equals negative 3, the function is not defined, so we can have either of those scenarios. All right, so notice that we have a jump discontinuity happening here at x equals negative 2. And then finally, we have an infinite discontinuity at x equals positive 2. So those are the locations of our discontinuities and the types of discontinuities that are occurring. Example 2 wants us to determine if f of x, defined by this piecewise function, is continuous at x equals 3. Explain. So remember from the definition of continuity, we have these three requirements or conditions, and in order for our function to be continuous at x equals 3, all three of those conditions must be satisfied. So let's go through them and check. All right, so I've written out the conditions here, and remember, in order for this to be continuous, all three of them have to be satisfied, otherwise the function is not continuous or discontinuous at x equals 3. So, does f of 3 exist? The answer is yes, because we see here that if x is equal to 3, then our output value is 6. So in other words, yes, because f of 3 is equal to 6. So I'm going to put a check mark to indicate that we've satisfied that condition. Condition 2 says, does the limit as x approaches 3 of f of x exist? So notice that anywhere x is not equal to 3, we have that our function is defined to be this rational function. So we can take the limit as x approaches 3 of 2x squared minus 5x minus 3 over x minus 3. And I'm going to go ahead and factor my numerator, and this will factor into 2x plus 1 times x minus 3, and I still have x minus 3 in the denominator. Then what can happen is we can cancel out the common factor in the numerator and the denominator, and then from here I can use direct substitution and say that we get 2 times 3 plus 1, which is equal to 7. So does the limit exist? Yes, it does. Now the final condition says that the limit as x approaches 3 of f of x has to equal f of 3, and notice that we've calculated f of 3 and we've calculated the limit, and these are not equal to each other. So notice that the limit as x approaches 3 of f of x is equal to 7, which is not the same thing as 6, which was the value of f of 3. So condition 3 is not satisfied. From here I can say, therefore, f of x is not continuous at x equals 3. So that's our conclusion for example 2. Example 3 says consider the function f of x defined by this piecewise function. Also, there is a slight typo here. This should not be here, and it should just say negative x plus 6. Find all values of x where f is discontinuous and identify their types of discontinuities, justify your answer, then sketch a graph of f of x. I'm actually going to start off with a graph to kind of help me identify where the discontinuities are. So let's start with this rational function here, and I can factor out x squared out of the numerator. So if I factor out x squared, I get x squared times x plus 2, and then x plus 2 in the denominator. Now, one thing that we want to be really careful about is I can now cross these out, and this is equal to x squared, but if I just leave it at that, those are technically not equal if we think about them as functions. In order for functions to be equivalent, they must have the same domain and the same range. So I need to caveat this and say that x cannot equal negative 2, because in the original rational function here, if I plugged in negative 2, then we would have division by 0. So I want to start to sketch my graph of this piecewise function, and I know that we have this when x is less than or equal to 1, and x squared is just a parabola that goes through the origin. And when I plug in 1 into x squared, my output value is 1, so I know that it's going to go here. I know that it's going to go through the origin, and then I just have to make sure that there is a hole when x equals negative 2. So here's negative 1, here's negative 2. If I were to plug in negative 2 into x squared, my output value would be 4. So I'm going to put a hole here, and then I'm going to go ahead and connect this, and my parabola is going to look something like that. And I'm also going to put an arrow here to indicate that it's going upwards, and the x values can go towards negative infinity. And then for the second part, we have the function log base 2 of x when x is greater than 1 and less than 4. So we can't, or our function's not defined by this logarithm when x equals 1 and x equals 4, but I can still see what the values would be if we evaluated this. So log base 2 of 1 is equal to 0. And then log base 2 of 4 is equal to 2. So those are where my output values would be, but I can put open circles at those locations. So here's 2, 3, 4. If I plug in 4, I'm going to put a hole here at 4, 2. So we can think of the ordered pair 4, 2 here, and here we could think about the ordered pair 1, 0. And so I'm also going to place an open circle at 1, 0. And I know that my logarithmic function is going to increase something like that. And then, let's see, our next row in our piecewise function says our output value is 2 if x is equal to 4. And so I can actually fill in this hole right here based off that third row in our piecewise function. And then the last one says if x is greater than 4, we have negative x plus 6. So if I were to plug in 4 there, I would have negative 4 plus 6, and that is equal to 2. And then that means that my graph would go through the ordered pair of 4, 2, but remember it's just greater than, but it was filled in earlier from the third row, and then from there we have a slope of negative 1. So I'd go down 1, right 1, and I go down 1, right 1. So this is 5, this is 6, and my graph will go down like that. All right, so looking at the graph now, let's identify the locations of any discontinuities and what type they are. There is a removable discontinuity at x equals negative 2. Notice that the function is defined everywhere around negative 2, but not at negative 2. There is an open circle there, so that is a removable discontinuity. And there is a jump discontinuity at x equals 1 because the limit as x approaches 1 from the left-hand side of our function is equal to 1, and the limit as x approaches 1 from the right-hand side of our function is equal to 0. And those are not the same value, so we have a jump discontinuity there. And that concludes example 3. So here we have two definitions for what it means for a function f to be continuous from the left at x equals a and continuous from the right at x equals a, and it's related to these one-sided limits. So example 4 says consider the function g of x shown below here, and part A says is g of x continuous from the right at x equals a, why, or how do we know? So it turns out that g of x is continuous from the right at x equals a because if we look above at the definition, in order for that to be true, the limit as x approaches a from the right-hand side of f of x must equal f of a, which in this case that does happen. And if we use the balloon analogy, we have our little person, they're walking along the x-axis and they're getting closer and closer to a from the right-hand side, and notice that the balloon is approaching this location right here, and because we have a closed or filled-in circle, we know that our function is defined there, and that value here is f of a. So again, this is continuous from the right at x equals a. So I'm just going to say yes here. All right, so let's move on to part B. G of x is not continuous from the left at x equals b because if we look above at the definition, the limit as x approaches b from the left-hand side of our function is not equal to f of b. And you'll notice that there's a hole there or open circle, and that's because here f of b in this scenario is undefined. So the limit cannot equal f of b since f of b does not exist. And that concludes example 4. All right, let's move on. A function f is said to be continuous on an interval if it is continuous at every number in that interval. If f is defined only on one side of an endpoint of the interval, we understand continuous at the endpoint to mean continuous from the right or continuous from the left. Notice that the previous example, g of x, is continuous on the interval from a to b, inclusive of a, exclusive of b, but not on the closed interval from a to b. Here's a theorem. If f and g are continuous at a and c is a constant, then the following functions are also continuous at a. So we have f plus g, f minus g, a constant times f times g, and f divided by g, so long as g of a is not equal to 0. Here's another theorem. The following types of functions are continuous at every number in their domains: polynomials, rational functions, root functions, trigonometric functions, inverse trig functions, exponential functions, and logarithmic functions. Let's use this in example 5. Example 5 says, where is h of x equal to this function continuous? Well, we have the sum of two functions. So we have this function here, and then we have sine of x. And this here is a rational function, and sine of x is a trig function. And according to this theorem, rational functions and trig functions are continuous everywhere on their domains. So another thing that we want to consider is the other theorem that says if we have two continuous functions and we add them together, then their sum is also a continuous function. So using these two theorems, we just have to figure out essentially think about their domains. And for sine of x, this domain is all real numbers. And for the rational portion, that domain is going to be all real numbers except anything that makes the denominator equal to 0. And so in this case, it will be all real numbers except for -1. And so to answer the question finally, we have therefore h of x is continuous on the interval -infinity to -1 union -1 to infinity. This next theorem says if f is continuous at x equals b and the limit as x approaches a of g of x is equal to b, then the limit as x approaches a of f of g of x is equal to f of b. In other words, so that's what IOW stands for, the limit as x approaches a of f of g of x is equal to f of the limit as x approaches a of g of x. Example 6 says evaluate this limit as x approaches 2. So notice that we have a composite function here, and really f of g of x is any composite function. And remember, a composite function is when you take a function and plug it into another function. So here we also have a composite function where the outer function is arc cosine. And based off the theorem that we just learned, we know that inverse trig functions are continuous on their domain. And so what we can do is we can apply this theorem right here, and we could rewrite this limit as the arc cosine of the limit as x approaches 2 of the inside function. In the numerator, I'm going to factor out the square root of x. If I do that, that leaves me with x minus 2. In the denominator, I'm going to factor out x, and that would leave me with x minus 2 as well. And notice that we can cross those out. And so using direct substitution now, we have the arc cosine of, I'm just going to plug in 2 into these using direct substitution. So we have arc cosine of the square root of 2 over 2. And this, if we think about our unit circle, is equal to pi over 4. And so there is our answer for example 6. This next theorem says if g is continuous at a and f is continuous at g of a, then f composed with g is continuous at a. So we're going to do something similar again. Here we have our outer function is a logarithm, and before we learned about a theorem that says that logarithms are continuous on their domains. So using that other theorem, again, we can say that this thing is equal to log base 2 of the limit as x approaches 3 of x cubed minus 11. Now, on the inside, if we ignore the logarithm for now, we can use direct substitution and just plug in x equals 3. And if we do that, we would get log base 2 of 3 cubed is 27. This would equal log base 2 of 16, and that would give us 4. So there's our final answer for example 7, and we were able to use that theorem again because log base 2 of x, that function, is continuous on its domain. The intermediate value theorem is sometimes abbreviated to IVT. Says, suppose that f is a continuous function on the closed interval from a to b, and let capital N be any number between f of a and f of b, where f of a is not equal to f of b. Then there exists a number c in the open interval from a to b such that f of c is equal to capital N. So here's a really cool visualization. And here we have f of a, here we have f of b, and here's a and here's b. So if I kind of just highlight those ordered pairs, here is, this ordered pair is a comma f of a, and then this ordered pair right here is b comma f of b. And we can choose any numerical value between the y values f of a and f of b, and if we have a continuous function, our function must attain that y value of n somewhere between a and b. We are guaranteed, and we call that x value c. And why is that? Well, I will often tell my students that the very informal definition of a continuous function is something where if you draw its graph, you do not need to pick up your pen or pencil to draw the graph in its entirety. And so if I have this location here as a starting point and this location here as an ending point, then somewhere between that, because I cannot pick up my pen or pencil, I must cross the y value that we are looking at. So let's use this in action. Example 8 says, use the intermediate value theorem to show that e to the power of x equals 3 minus 2x has a solution on the interval, on the open interval from 0 to 1. So what I'm first going to do is I want one side of this equation to equal 0, and we'll talk about in just a moment why we're doing that. But I have e to the x, and then I'm going to add 2x to both sides, and I'm going to subtract 3 on both sides, and that means that the right-hand side of my equation is going to equal 0. Now what I'm going to do is I'm going to think about this thing here as a function, and I'm going to call it h of x. And notice that h of x is the sum of two functions. First off, we have e to the power of x. This is an exponential function. And then we have 2x minus 3 here. That is a linear function. And exponential functions and linear functions, unless we restrict the domain, always have domains of all real numbers. And before we learned about a theorem that says that exponential functions and linear functions are continuous on their domains. So by previous theorems, h of x is continuous for all x because it is the sum of two continuous functions. Now, why do we have to write all that? In order to use the intermediate value theorem, it says that the function that we're looking at must be a continuous function. So we have to satisfy the conditions of this theorem. Now, where do we go from here? Well, I want to now think about the graph of my function. So here's my y-axis, here's my x-axis, and I want to show that this function now is equal to 0 somewhere between x equals 0 and x equals 1. So let's just say we have x equals 0 here and x equals 1 here. Now, what I can do is I can evaluate my function h of x at x equals 0 and x equals 1. So let's go ahead and do that. So I've gone ahead and I've plugged in x equals 0 and x equals 1 into my h of x function, which remember we defined to be e to the power of x plus 2x minus 3. So this thing here is my h of x function. And notice that the output values for h of 0 is -2, and then for h of 1, that's equal to e minus 1. And the important part here is to recognize that -2 is a negative number, and e minus 1, because e is approximately 2.71, this thing is a positive number. And so what we have then is, let's say this is -2. I know that my y value is here, and then at 1, my y value is positive somewhere. And so just again for a visualization, if this is my starting point and my end point is over here, I have to cross the x-axis somewhere between 0 and 1. And I don't know exactly where that's happening. I just know that it's between 0 and 1, so it could even look something like that, and maybe our c value is there, but I do know that it exists and it's somewhere between x equals 0 and x equals 1. So let's put this all together. I definitely need to name drop because I need to identify this theorem and name drop it. And I also need to talk about f of a and f of b, which in this case a is equal to 0 and b is equal to 1. So since h of x is continuous and h of 0 and h of 1 have opposite signs because one is positive and one is negative, by the intermediate value theorem, there must exist a value of c on the open interval from 0 to 1 such that f of c is equal to 0. And that completes our proof using the intermediate value theorem. And when we're done with a mathematical proof, we'll put some kind of symbol to indicate to the reader that we're done. This is the symbol that I use. Some people will use a square or a box, fill it in, or leave it unshaded. And another common one is QED for ending a mathematical proof. And that concludes this section on continuity.